Dan Olds here, and this is the second stop on our epic 2022 Great American Supercomputing Road Trip. And where else to revisit but Idaho National Laboratory? We are here with Eric Whiting, and is that your last name, Whiting? Yes. Yep. I'm sorry, my screen is really small here. And we've got Mathew Anderson. How are you guys doing today?
Doing great. Good to talk to you again, Dan.
Great. Yes, we were there in 2018 for the first ever HPC road trip. We're going to try and do it again this time, but better. So let's see what we can do. I guess what I'm looking for first, let's talk a little bit about the lab and the unique mission that you have.
Idaho National Laboratory is the premier nuclear energy laboratory. Premier in the sense it's the only nuclear energy laboratory. It supports multiple industry players as well as university researchers in support of clean energy through nuclear power. The laboratory itself supports it's the only site where supercomputing is uniquely dedicated to nuclear energy research. Idaho National Laboratory maintains 150,000 plus cores, a lot of GPU computing, of which, of the systems we maintain, 80% of those cycles go directly towards supporting nuclear energy research. About 10% of those cycles will support some form of renewable energy research, and then a mixture of other projects for the rest of it. So it's most of the computing here is supporting nuclear energy, and the laboratory is built around enabling energy security for our future through nuclear energy, nuclear power.
Excellent, excellent. And actually, you segued right into my next question. What sort of compute resources do you have? I believe that you stood up a brand new system since I was last there in 2018, right?
So we've set up really two systems since you was in 2018.
Good job.
A 20,000 core OPA network Dell system named Limhi, and then a nearly 100,000 core HPE system named Sawtooth, which was arrived in 2019, deployed to users for general use in March of 2020.
And a new building as well, right?
Yes, a new building, with the 7,000 square foot data center, as well as offices for researchers. So it's a combination of data center as well as office research facility that looks a lot like a university campus in the sense it's very open and there's lots of collaboration. It was built as a collaboration facility where HPC professionals can interact closely with modeling and simulation experts and domain science users.
You've got to be pretty proud that came home, Eric, because we were just looking at the plans and the shell of the building in 2018.
Yeah, Dan, last time you were here, you were looking out, I think they were pouring concrete and putting up steel.
Yep. And
it was an exciting time, and now we've moved into it. And I'll say it's the best building on campus. We have and officially we have maybe 500 buildings across the whole campus. This is the best one. It's
fantastic.
like Matt said, it's very collaborative and open. It's been very instrumental in helping us bring these new computers online. And I'll just add maybe two trivia kind of statistics about the building.
Sure.
The people capacity is close to 200 people. That's kind of, the design was roughly 200 people. And when we look at the data center and the footprint of the rack layout in the data center, it was intended to support roughly 200 racks. So in a silly kind of coincidence, a rack of computing.
Rack a person.
Yeah, but of course that's not how it really works. But
there were some researchers that would be offended by that. What, I'm only getting a rack?
Yeah.
But that's very cool. Very
and I should and just I'll just fill in one other piece of global picture is the laboratory right now has roughly 5,500 employees spread across a lot of different sites. We're part of the town campus, and the town campus is probably 60% of our employees.
Okay. And that's the campus I visited.
Yes.
Yes. Okay.
And
So,
let me
go
add,
ahead. Yeah.
in terms of the computers itself, we support about 1,200 plus users. And so not every single employee at Idaho National Laboratory actually uses the HPC systems directly, but many benefit indirectly from the simulations that happen here actually directly support multiple experiments that are ongoing. So it's not a one-to-one for every single employee. Is there actually a person using the HPC account? And then almost nearly 50% of our users are actually not INL employees. So they will come from the nuclear energy industry and university users. So all the major players in nuclear energy have accounts here, as well as their university collaborators, as well as INL university collaborators.
I mean, you've got to be the single largest resource for nuclear energy computing in the country, for sure.
Certainly the largest free resource.
Free resource, even better.
We give our cycles for free to nuclear energy researchers as well as industry users.
Excellent. So let me ask you this. We have all of this on site, a lot of capacity there. Are you utilizing the cloud at all, or is that in your plans?
We provide, there is some cloud usage for certain types of experiments in which the data is currently stored in the cloud. However, that will change. The data resources will eventually move. We'll become more and more like a cloud operator. The HPC systems here ourselves, and where nuclear energy resources and researchers can store data and release data to the public via the storage capacity here, simply because we provide our cycles for free and it doesn't take a credit card to move data.
So in essence, the public cloud usage today is more of a stopgap until you're prepared to
That's
do
what
it.
we anticipate in the near future.
Okay, that makes sense. And you mentioned GPUs. How many systems are accelerated, and is it only GPU acceleration or any other types?
So the Sawtooth, the HPE system installed delivered in 2019, installed 2020, has 108 V100 GPUs that are principally used for machine learning type operations and some molecular dynamics simulations along the lines of GROMACS. And then there's certainly some density functional theory happening on those GPUs as well. In general, the nuclear energy industry is risk averse, and so most of the codes you find for nuclear energy, transient testing, compliance testing are not well suited for GPUs at this time. And that's certainly true for Monte Carlo simulations as well. They just don't do well on GPUs up to now. And so the GPU usage is mostly, the Sawtooth system does have a significant component of GPUs on it. The usage generally lies along the machine learning type applications, or a few of those like NEC-RS applications that are computational fluid dynamics simulations that are well suited for GPU type operations. The bulk of the simulations that occur at Idaho National Laboratory are along the lines of Monte Carlo, which just simply don't do well on GPUs.
Well, that leads me into my next question. When I was first there, we talked quite a bit about using machine learning to inform your simulations and be able to cut down on sort of the brute force that you'd have to use in changing parameters and things. It sounds like that's been coming along pretty strongly.
There are certainly efforts in that direction to reduce the modeling and simulation efforts to support, supported by one-shot learning, or certainly along the lines of what the VASP toolkit did with accelerating density functional theories by evaluating whether or not a simulation actually had to proceed, or whether it could be estimated from or inferred from some sort of machine learning model. These are really research stage at this point, not production level.
Oh, real? Okay.
Not production level systems yet. Production level code sets yet.
Okay. Okay.
Well,
but
Dan, I'll just add one other thing. I think Matt mentioned our GPUs in the Sawtooth supercomputer. We also have a laboratory resource with 44 A100s in it called Hoodoo. I'm not sure Matt mentioned that, but but we do have other systems that are heavily used, and we'll grow that capability depending on the needs of the researchers and
Sure.
the capabilities of the codes. I believe we have a good foundation, and we're developing expertise in that area, and depending on needs and capabilities, that will continue to grow appropriately.
Very good. This is kind of a interesting question, this next one, that we're seeing a lot of changes, at least proposed changes, coming along the lines of CXL, that sort of thing, composable infrastructure. Is this anything you've been investigating yet?
Composability has been a key tenet behind the Moose framework, and obviously has generated a lot of interest in terms of architectures, architecture agnostic type development. In terms of deployment, though, we have not. There's certainly research in that effort in that direction, but in terms of, we're also concerned about very production level type codes,
sure,
support of nuclear energy, and so we're not seeing that at the production level phase yet, but certainly around the research phase, and it is generating a lot of interest. Composability is a key tenet of the Moose framework, which is the core behind 21 different nuclear energy applications.
Okay, that's good. I wasn't aware of that. And today it's kind of limited in scope, in that I think you can probably assemble some large pools of memory from non-physical systems, but I don't think we're at the point where you can do GPU sharing or anything very easily.
The Moose framework doesn't support GPUs at this time, but we certainly, the ability to say, compose a node that has like 20 GPUs on it.
Yeah.
That's it's intriguing.
It is, isn't it?
It's intriguing in terms of also storage, actually using it as a storage solution, composable storage. It's generated interest, and there may be roles in composability, integrating that directly with the Moose framework. Again, that's what I mentioned. It was built around the idea of, composable software integrating with potentially composable hardware. But at this time we don't have any hardware that can support anything like that.
Yeah, so the industry doesn't at this point.
It's interesting. It's certainly probably more interesting for the machine learning folks, just as simplifying some of where they, do they address model parallelism or data parallelism? What is their particular approach for their method for extracting concurrency and being able to create composable hardware may impact some of the way they think about how to extract concurrency when training the model.
Very cool. How about quantum computing? Any thoughts along those lines?
We did participate in the IEEE Quantum Conference in Denver just in September. We've been watching it closely. We do not see at this time any direct application to the nuclear energy modeling and simulation efforts.
Yeah, that makes sense to me. Let me ask you something even farther out then. When are you going to get your first Exascale supercomputer?
I think the real question is, when do we develop the first Exascale software application for nuclear engineering? We're not concerned about LIMPAC here. We are concerned about delivering clean energy and through accident tolerant fuels, through low cost microreactors, modular reactors, and proving those fuels, developing examining the transients. These are the fundamental science questions that we want to answer. The HPC is not a solution looking for a problem here. We have very specific problems, and the hardware is designed around the problem, and not we're not trying to shoehorn a solution into a problem.
So we're not going to shoot for the charts just to shoot for the charts.
No.
Good.
The fundamental goal is, and the real test is being able to deploy advanced reactors, advanced fuels, and ensure compliance, regulatory compliance, safety, and make them economical. These are the key tenets. And if exascale computing is required for those to achieve that, we will absolutely have an exascale computer.
But not before.
If not. And if we do not, there's a lot of aspects that go into this. There's a lot of experimental work, which the HPC system supports. So it's not just modeling and simulation. There's also, the compliance testing to be able to even conduct some of these experiments that give us the key data points for understanding the behavior of, say, how does a triso fuel particle degrade over time, and the type of or the types of the behavior of fuels over time. The xenon gases, for instance, and how those ultimately impact the fuel storage and fuel recycling even. So these are the questions we're trying to address, not how to achieve an exascale system.
Yeah.
When, as we see, obviously we don't want to drive from the rearview mirror. We want to deliver the technology that will help drive, move the modeling and simulation forward. But we don't want to get too far ahead of the modeling and simulation such that the systems become useless.
Yeah, makes sense. I had to ask, though. I mean, with
Dan,
all the buzz.
Yeah, and Dan, I would just add that I think Matt's answer was the best ever answer I've heard to our strategy for exascale. I think that he did a very good job of explaining it. There's maybe one other way to answer the question, and that is in terms of just technology trends that people in your field watch, and we watch carefully. How is density and efficiency and functionality, increasing vectorization and stuff, how is that impacting what we buy in terms of compute systems? So that's another dimension of this evolution. And as we look at our data, as we look at the top 500 data, we see that a lot of the computers we buy are kind of, let's just say our computers are maybe eight years behind the number one system, maybe 7 to 9 years behind the number one system. So if those trends continue, which they may or may not, it might be another answer to your question, when will we have exascale, might be, well, 7 to 10 years from now, we might have that capability if industry trends continue, which is uncertain. That's
an interesting answer. That's something for us to put a bookmark in and come back to later on and see. Well, let me, while we're talking about systems and things so deeply, let me go ahead and ask you this. Let's assume that you're addressing the entire vendor community right now, the HPC vendor community. What is it that you need from them, say, 3 years down the road? What do you need? What do you want?
We obviously want more bandwidth, more memory bandwidth, and less power, and so less power consumption. I think the real answer is that we'd really like systems to be more specific to the application, almost application-specific type systems. If you could create an ASIC for Monte Carlo, Boltzmann type transport simulations, we'd love that. That'd be the lowest possible power, the best possible performance. Our codes don't change a lot. They're really production level. We would like systems almost built specific to the type of applications that we're running to get the best possible performance, the lowest power consumption, and the best price. So almost application specific type systems.
Would you be interested in an FPGA solution that could do Monte Carlo, for instance?
Well, we've already invested heavily into several FPGA solutions, and we do actually have quite a few FPGAs deployed here. FPGAs are a step towards ASICs.
Yeah.
There's some things they do not do well. They, of course, do deep pipeline parallelism extremely well. They're very useful for inference, machine learning problems. They're very low power, and the register transfer layer, the RTL, is certainly a step towards creating an ASIC. Now, getting a Monte Carlo, full Monte Carlo type simulation, solving a Boltzmann equation onto an FPGA is extraordinarily difficult, and largely because FPGAs do well with integers. They do not do well with FP64, which is what we would need for an application-specific solution for, say, Monte Carlo simulations. So are FPGAs ready for the task? No, they're not.
Okay.
You're not going to be able to suddenly get get magic performance with, because if it were all integers, sure, it would be great. FPGA would definitely win if they were all integers. We're not talking about integers in this situation, so we'll see. We'll watch it closely. Obviously, we do use a lot of FPGAs here for other things, but not for Monte Carlo.
Okay. What do you think, Eric? Same question.
Yeah, I guess one of my wishes, well, first of all, again, support what Matt said. That was really good feedback there. I would say from a system architecture standpoint in the HPC world, it would be extremely beneficial if our vendors would standardize on a cooling strategy. If we could, it feels like as I look at the landscape, as we look at what people are trying to do, it feels like this evolutionary process of converging on a good cooling strategy is not converging to any solution. I'd love to see standard temperatures, flow rates,
standard connections,
interconnections. Look at what the standardization did to I guess 40 years ago or 30 years ago in the development of the PC. Just having some standards helped a community kind of develop capability. And right now, cooling is an impediment to production HPC, and it's not standardized.
Are you liquid cooled on your systems today?
All of our systems use liquid cooling to some extent. The Sawtooth machine is direct liquid cooled to the processors and the switch network. The rest of our systems, we bring liquid cooling right to the rear doors.
Okay.
And that's still air. It's an air liquid transfer,
but it's a step that helps.
It's closer to the system. It's closer to the heat source. So, some kind of improved standardization in, like I said, temperature and flow rates and water temperature, that is water temperature, water flow rates, and the water interface. It's amazing as we work with our own system and we talk with peers. Water, we didn't think we'd have to be water experts to run a computer.
Plumbers.
We didn't think we'd have to be plumbers, but in this day and age of HPC, we end up having to do more plumbing than we'd like to.
And the TDPs are only going up.
Yep.
And that's going to make this even more critical down the road. Yeah.
Note that becoming a plumber also means becoming a chemist and a biologist to understand what's in the water.
Yes. And to make sure that nothing gets in the water, nothing grows in there, that sort of thing.
Yep.
That's important. So now, are you both going to SC22?
Yes.
Excellent. Is there anything that you're particularly looking forward to either seeing or talking about or hearing about? Or
something that's always helpful to me, Dan, I like looking to see how the vendors are, how they're packaging processors and memory, how they're fitting them in a rack. I'm very interested in, I guess I'm very interested at that level, what solutions the vendors are coming up with for deploying the hardware. I'm also very interested at the semiconductor level. What are the changes happening in processor and memory and network? Where are people evolving? Where are people what changes are happening? If you look at the top 500 list over 30 years, you see a lot of evolution.
Oh, yeah.
A lot of kind of moving back and forth. And I guess that supercomputing conference is very useful in watching that and getting a sense of that.
And to just reiterate, the processing of memory is a high interest of mine, as well as the solutions to see what is being packaged for direct liquid cooling of memory.
Okay, that is good. Well, I want to thank you both for your time. Really appreciate it, and appreciate you getting on the horn with me virtually so we could talk about this. And it's going to be a very interesting interview. Really appreciate it.
We love your questions. We love working. Love this opportunity to talk to you too, Dan. Thanks.
Great. Thank you.
Thanks, Dan.
Okay.
500 miles of open